bit more if I had a machine gun. And I shot it at a double slit with a wall in behind it. We'd shoot a bunch of bullets here. A bunch of bullets would land here. We might have some bouncing off. Some bouncing off. Probably mostly just two places where all the machine gun bullets would hit. That makes sense, right? Okay. Now, what we did in class, or actually using water might be a better way to show you. I actually remember showing you this. If we have a wave coming in to a wall with two holes in it, a water wave hitting it, each of these openings are a point source for a new wave front. And we go like this and create that new wave front for each of them. Something like that. And if you remember, we have constructive interference patterns where they cross, something like that. And so over on the screen here, actually when we use the lasers, we just saw a bright central spot and then the dots going out, right? So that was constructive interference, and in between is destructive interference. So this is how a wave function works. So we have particle function like a machine gun, wave function like water or a laser beam. Okay? So when we're firing a beam of electrons, what do we know about electrons? Where are they?
Particle.
They're little particles, like little BBs, little pieces of matter, right? So when you think of those, that's kind of what you think of. So our expectation would be, when we're shooting the electron beam at here, would be what? Wave function or particle function?
Wave.
You're just throwing that out there.
Well,
The expectation would be particles,
it's
right?
physics.
Yeah. It's confusing.
Good job, Michelle.
So we'll say we're going to shoot the electron beam. One would expect it to be machine gun-like, and you'd have this particle function hitting the screen and back. Of course, that's not what happened. We had a wave function. It acted just like this, just like the laser beams, and had the central bright spot, and it continued out. Well, that was kind of confusing because we thought we knew what electrons were, and how can electrons act like waves? That doesn't make a whole lot of sense. So instead of just shooting the full beam, we're just going to shoot one electron. Now we'll get this figured out. So the second thing we do is single electron. Obviously, that one electron is going to go through one or the other of the openings, and it's going to look like a particle function in the back. Obviously. Except that it interferes with itself. And forms a wave function on the screen. It's a single electron. Okay, that totally does not make any sense.
Is there an explanation for this?
Yeah. It is what it is. So what do? Oh, we have an idea. We're going to see what happens to it. We're going to put a little detector here. Shoot an electron. And we know that when the electron goes through that opening, the little detector is going to go, boop, went through here, and you know. That makes sense. So what was it? When it went through this opening with the detector on it, it was a particle. But if it went through the opening that didn't have the detector in it, it was still a particle. Okay, now we don't like this. We get it if it's a particle that makes our little detector light go on. But it acts like, when it goes through the other opening, it acts like it knows the detector is here. We don't like it.
So without detector, it was particle function as well. They were both particle function. Even when the detector wasn't there.
Went through the detector, it was a particle. Went through the other opening without the detector, it was also a particle, as if it knew that there was a detector in the other opening. Well, did we make a mistake? Take the detector out? Still away. Put the detector in the other one. Particle, particle.
That's weird.
If you're the scientist running this experiment, what conclusions can you make out of this? Number one, electrons can see and think. I kind of discount that one. But maybe, who knows?
Let's go for that. I like that way.
The other one is that matter itself exists both as a wave and as a particle. And that's the one we're going to decide on. That's the one we're going to go with. Does that make it any easier to understand? No. Nope. It doesn't. But that's a big part of quantum physics. Wave-particle duality. Not just electrons, but all matter exists both as a wave and as a particle. Science books a few years ago talked about that, and they say that in the macroscopic world, the world in which we live, that the wave function part of matter just exhibits itself a little teeny bit. So we'll go with 1%, and then 99% is just stays a particle. When we get down into the quantum world, the subatomic world, then it's a 50-50 deal. It can exist in a wave and a particle, and it's about half and half. Anymore, physics says that maybe the most stable form of matter is its wave function. And it doesn't matter how large it is. Maybe everything exists as a wave. We'll talk more about that later. And you won't like it.
Goody.
The next part of this is another ugly part of quantum. The next part of this is that you, the experimenter, are an integral part. You can't be an outside observer. When you observe something, you make it a reality. When you look, you cause it to be.
So, if a tree falls on the forest and nobody sees it, it actually doesn't exist.
Just think about this. A double slit experiment by itself is set up to look for what? Waves. That's what a double slit experiment is. That's what we looked at in this classroom. We use diffraction gratings, but they do the same thing. It looks for waves. It looks for interference pattern of waves. I set the experiment up to look for a wave pattern. Did the electron really have any choice? When I put a detector here, what am I looking for? I'm looking for that little ball bearing. I'm looking for that little BB electron. What do I get? The little electron. The weird part is when it goes through this one. But I still have a detector there. I'm still looking for that little BB. My observation is looking for it, and that's what I get. To put this more in a perspective that ends up being a real life sort of situation, back in the 1960s, early 70s, DDT, an insecticide, was used pervasively all over. And it was discovered that it caused birds' eggs to become thin. And it may have been the cause of the eagle population to die out for a while and become endangered. They're not anymore. Some biologists were studying a group of eagles. Their nests were up on this cliff, and they wanted to see if DDT was in their eggshells, or to test whether their eggshells were thin. They couldn't access this cliff from below, so they accessed it from above with helicopters and people climbing down ropes. And they'd get down to the nests, and they would measure the eggs. They'd go back up, come back a week later, measure the eggs, and discovered that, yes, indeed, the eggshells were thinner. When they wrote up the report, they said that DDT is pervasive, it's everywhere in the world, it's causing eagle's eggs to be thinner and probably the cause of the eagle population dying out. A pretty good conclusion. Problem is, someone else looked at their data and looked at their experiment and looked at their results, and their conclusion was this: when eagles are nervous, their eggs that they produce have thinner eggshells. And the result of this experiment was a bunch of helicopters flying around and people climbing down to your nests on ropes makes eagles nervous. Thus, they produce thinner eggshells. Without meaning to, these biologists put themselves in the experiment. And if you think about any experiment, when someone sets up an experiment, they set it up to look for something, don't they? There is a purpose behind it. They have a hypothesis, they want to prove that hypothesis. The experimenter is always a part of the experiment. You can't separate yourself. And your observation of an event makes that event. How would you look at an electron? What is the way, what method would you use? Well, you kind of have to shine a light on it. Well, a light is a photon. A photon hits an electron, it makes it different. It changes it. And what they call that is coalescing the wave function into a particle function. Your observation of it changes it. You become part of the experiment. You become the observer. Gotta love this, don't you? In your packets, it also talks about something called quantum entanglement. Did you read about that yet? It's in the next couple of, they're up here, you'll get it in a second. Have I shown you pictures of particle collisions? Yeah. The background of this poster right here is a proton, anti-proton collisions. So these little swirls in this orange background. I'll find you one.
It's in our packet. There's like a picture.
Yeah, and I'll find you maybe a better one. In those particle collisions, out of nowhere comes particles, and sometimes they come as a pair. At times there's a positron, which is a positive electron, and an electron pair. When those pairs are produced, they're connected in some way. They call them being entangled. What's really interesting about that is if we separate those entangled pairs of things, and it doesn't matter how far away we put them, if we do something to this one, it affects this one at a distance, instantly. We could even take one, keep it on the Earth, take the other one, put it at the other end of our galaxy, and we tickle this one, and that one laughs. Instantly. They've proven this.
They tickle.
They didn't tickle it. They put it on the other side of the Earth. That's good enough. In your packet, it talks about the Einstein-Rosen paradox. And that's what he's talking about. He said, this is ridiculous. That means faster than light communication, that cannot happen. Well, it happens. It's true. Impossibility occurs. Somebody this morning was saying, well, if that's true, why can't we develop that as a communication device? You could talk on the phone to somebody on the moon with instant communication instead of the minute and a half time lag of whatever it is. To the sun, it's an 8-minute light time lag. To the edge of our solar system, it's a 3+ hour light time lag. And then, et cetera, as we go on from the Earth. Why can't we develop that as a communication device? Probably because those particles are very unstable. So instead of listening to me all period, I'm going to let you listen to Dr. Quantum, because he's a pretty good
Dr. Quantum.